Okay, Assalamualaikum, and this is our lecture video for the chapter 2. So for this video, we are going to learn about the subchapter 2.1, solidification of pure metal and alloys. Okay, so the objective of this chapter is to understand the phase transformation during solidification process, differentiate between cooling curve for pure metal and alloys. Okay, so let's get started. First of all, you have to know the terminologies that found in this chapter. Okay, so let's start with the solvent. Solvent is an alloy, the element or compound present in greater amount. So solvent with greater amount, solute is in lesser amount. So if you have solutions, solution is when two components combine to form a single phase. Okay, phase here means that solid, liquid and gas. So the solutions mean that it must be in a single phase, either in the liquid, solid or gas. Okay, solubility, the degrees to which the two component mix. Okay, how good they are to be mixed together. So that is the solubility. Okay, solubility limit. Okay, when it comes with the word limit here, it means that it is the maximum concentration of solute that may be added without forming a new phase. Okay, so here solvent, greater amount, solute in lesser amount. Okay, so solution when you mix or combine two components to form a single phase, and so on lah. Okay, and then components. Okay, here components are the elements or compound which are mixed initially. As example, aluminum and copper. Okay, phases are the physically and chemically distinct material region that results example of alpha and beta here. Okay, so from under microscope here we have different region where alpha here represented by the darker phase and the beta phase here is the lighter phase. So as example, let's say you have a liquid only, so it only has one phase. But if you have one is the liquid, pure liquid, and the other one is the alpha or sometimes alpha solid, so here now we have two phases. Okay, so so in this picture here shows that you have two phases. One is the beta and one is the alpha. Okay, and at the bottom note here, note that solid, gas and liquid is also a phase. Okay, and then we go to the solutions. Okay, we go back to this slide. The solution is when two components combine to form a single phase. And then here the solutions, when two components combines, they can either remain separate or combine to form a single phase, which is referred to as a solutions. Okay, it is the same meaning, okay, as we discussed earlier. So here the solutions in this one, right? Okay, when you combine two components where the component is the solute and this is the solvent. Okay, and then we know the solvent is the higher amount. So the higher amount here is the solvent and the lesser amount is the solute. So kalau awak nak bancuh air Milo, yang ini adalah air masak, air suam. Ini adalah Melo. Okay, so the Melo is the solid and the water, plain water, is the solvent. And then when they mix together, they combine together to form a single phase of liquid, so it become the solutions. Okay, let's say this is the these are the examples, so you can read by your own. Okay, so if two liquids dissolve together like alcohol and water, they are said to be miscible. Miscibles mean boleh bercantum lah, boleh boleh masuk, boleh larut. Okay, miscible. If not, then they are characterized as immiscible. Okay, macam air dan minyak memang takkan boleh campur. So that if it can be soluble, can be mixed, and then we can dissolve, so we call it miscible. If they cannot be dissolved together, so it is immiscible. Okay, so these are the common types of solutions. Okay. So we go back, we go to the next slides, the title of metallic solid solutions. Okay, most metals are combined to form alloy in order to impart specific characteristic. So here, I hope you know what is alloy. Alloy, okay, here is a combination of two or more elements. Added impurity atoms, at least one, which is a metal. So at least one is a metal. If two of those elements are not metal, so it is not alloy. It is just the composite. Okay, alloy only specific for the metal combined with the other elements. Other elements also can be a metal elements or not. Okay, so there is the combination of two or more elements where at least one is a metal element, so that we can call it alloy. Okay, so the addition of impurity atoms to a metal will result in the formation of a solid solutions. Okay, the addition of impurity atoms to a metal will result in the formation of a solid solution. So a solid solution is a solid state solution of one or more solids in a solvent. Okay, example: steel, cast iron, brass, aluminum alloy, nickel base alloy, magnesium base alloy, titanium alloys, and so on. Okay, so here, which one is the solid, which one is the solvent? So we know the solvent has the greater amount, so it must have the highest amount of atoms here. So the white here must be the solvent, and the solid, okay, here is the lesser amount, the blue one. So the blue one is copper, yes, solid, and the solvent is nickel. So nickel, copper, solid solutions. So we call it substitutional solid solution, because it just substitute the space. Okay, okay, where were we? Oh, the substitutional solid solutions, because we have two types of the solid solutions. One is the substitutional solid solutions here, and the other one is interstitial solid solution. Okay, so substitutional solid solutions, based on the Rotary rules. Okay, the rules tell us how to know that either it can be form of a solid solution or not, where you combine where you combine two or more elements. Okay, the conditions that based on the Hume-Rotary rules, property of the atomic radius must be less of 15% difference. Okay, so the size of the atomic radius of between one element and the other element must not more than 15% difference. Okay, so this is the example that you can write in your notes. Okay, I know it is just a blank space in your notes, so you can copy from this slide into your notes, write down into your notes. Okay, crystal structure. Okay, the same crystal structure, so the conditions must be the same, similar type of crystal structure between the elements of the alloy. Okay, so if it is the solvent, the green one, if the solvent is BCC, body centered crystal structure, so the other elements which is solid must be also BCC. If not, you cannot have the rules here. You cannot obey the rules, so it cannot be the substitutional solid solutions. And for the electronegativity, it also must be similar electronegativity or smaller in kind of very small difference electronegativity. Okay, so and the final rule is the valence electrons, the numbers of electrons at the most outer shell also must be similar. So if the solvent here has 6 electrons valence, and the solid element also must have 6 electron valence. So if all the rules here are obeyed or are completed, are followed, so then it can be called the substitutional solid solutions. Okay, so here the difference between substitutional solid solution and the interstitial is where the atom of the solvent is replaced or substitute, so that's why we call it substitution. Substitute with solid impurity atoms here. Okay, so note here, not all alloy systems that fit this rule will form appreciable solid solutions. So it not 100% rules that you can follow lah. Okay, so example here is the copper nickel system. Both metals are completely soluble. Okay, here this is the example, so you can write down the answers. So the answers here is the completely soluble in each other because all the requirement of Hume-Rotary rules have been satisfactorily fulfilled. So the solid phase is a substitutional solid solution. How do you know it complete all the requirements? Okay, so we have to check one by one. So the rule 1 is the atomic radius. You find the size of atomic radius in the textbooks, or you can also find the internet. So we know that the size of copper is 0.128 nanometer, nickel 0.125 nanometer. So the difference between the size of radius is only 2.3%. So it obey the requirements, the rules here, because it cannot be more than 15%. So we have only 2.3, so it just nice under 15%. Okay, So the second rule is the crystal structure. It must the copper and nickel must have the same crystal structure. So the copper we know we share in the textbooks or in the schedule or in the internet. We found that it is a face centered. So FCC, and then nickel also FCC, so it is similar. So it follow or it check the rule, the second rule here. And the rule 3, negativity, electronegativity. So the difference between the electronegativity is only about 5.2%, and the valence electrons also +2 and +2. So 2 electrons valence for the copper and also of the nickel. So it can be followed. You can follow the rules of number 4, the valence electron. So it check all the rules. So now we know it is completely soluble because it is very fulfill of the requirements, and from that we know it is substitutional solid solutions. Okay, and we go to the next example. The copper and argentum. Okay, both metals are partially soluble in each other. Okay, it is not the completely soluble compared to this one. It is just the partially soluble. Why? Because they not check all the rules. Only partially rules are fulfilled here. So we see here the rule 1 check only 9.4. The same crystal structure, and electronegativity only around 5.2, but the valence electrons here are not the same between the copper and argentum, so it do not check the rule number 4 here, the valence electrons. So it is still the substitutional solid solution, but it is partially soluble, not completely soluble, because one rule here it cannot follow. Okay, so here we expect that argentum and copper will have limited solubility. Okay, let's have a break of 5 minutes. I have to go to the toilets. Okay, now I just paused the recording video. Okay, we know before that we have two types of the solid solution. One is the substitutional solid solution, as we discussed before the break, and now we have to learn the other types of the solid solution, which is called interstitial solid solution. Okay, the interstitial solid solution exists when impurity atoms fill the voids, fill the space between the atom here, the voids, we call the voids. So in the solvent atom lattice, so the green one is the solvent atom, and then the solute is the blue one here, fill the void between the solvent atom. So that's why we call it interstitial. Okay, atomic radius of an interstitial impurity must be smaller. Of course, it must be smaller because it must have the solute atom only have to fill the void, so it must be very small compared to the atom of the solvent. Okay, normal maximum allowable concentration of interstitial impurity atom is low, below 10%. Normal maximum allowable concentration of interstitial. Okay. The atom of the parents or solvent metals are bigger than the atoms of the solute metal. In this case, the smaller atom fit into space between the larger atoms. Okay, this structure is known as, this example shows iron carbide. So iron is the ferrum. Okay, carbide is the carbon, so FeC3, And then the solvent here is the ferrum, okay, iron. And then the solute here is the carbon. So in this case, the smaller atom, which is the carbon, smaller one, fill the space, the void between the larger atom, where the larger atoms is the ferrum or iron. Okay, so here the solubility limit. Okay, now we go to the solubility limit. Okay, solubility limit is the maximum concentration for which only a solution occurs. Okay, so if go beyond the numbers of the concentration here, maximum concentration, so it cannot be soluble again lah, cannot be soluble lah. Cannot be soluble no more. Okay, so here the question of the example asks you to find what is the solubility limit at 20 degrees or Celsius. So this is the example diagram of the solubility limit. Okay, to find the solubility limit, so you find the temperature 20 and then you project the line to the graph of the solubility limit, and then from here you track down to the x-axis to find the composition of sugar here. So here we know that 65%, so that's why the answer is 65% of sugar. Okay, and then what happen if the composition is less than 65% at that point? Okay, here at that point on the left side, before the line here, before the solubility limit line here, is the on the liquid solution, L here, liquid solutions. Or here we know that with the sugar and the water, we know it is called the syrup. So here is only in the syrup phase, liquid phase. But on the right hand side here, okay, on the right side of the line is on two phases. One is they are in the liquid and also in the solid of sugar, because here sugar is no more, it's not yet soluble with the water. So this is the limit of the solubility. So on the right side it cannot be soluble more, no more. Okay, and the left side it is soluble. So here is the limit. Okay, so solubility limit increases with temperature T here. If temperature is 100 degrees Celsius, yes, here solubility limit around 80%. So if I project the line, macam itulah, lebih kurang lah, tangan saya bengkok. Okay, so this is how you find the solubility limit. Okay, so let's go to the next slides of solidification. Solidification ni pembekuan lah. Solidification is the most important phase transformation because most of the metal alloy undergo this transformation before becoming a useful object. Okay, so kita tahu tadi bila kita nak buat alloy, apa alloy tadi? Alloy adalah metal campur non-metal ataupun metal campur metal elements, kan? At least salah satu metal. So lebih daripada dua elements dan salah satunya adalah metal, itu adalah alloy. Okay, bila kita nak cantum alloy, biasa cantum alloy tadilah kita belajar cantum alloy dalam keadaan solutions. So we have also learned about two types of solutions here. Satu substitutional, satu lagi interstitial. So dia combine, dia cantum alloy waktu dalam bentuk keadaan solution, dalam keadaan liquid lah, lebih kurang. Tapi bila dalam keadaan liquid, kita tak boleh pakai sangat untuk objek, untuk jadi produk. Biasa kita kena tukar dia jadi solid, dalam bentuk solid lah. Sebab itu kebanyakan kita jumpa alloy-alloy besi-besi, alloy stainless steel contohlah, macam-macam lah kan. Okay, semua tu dalam bentuk solid lah. Sebab tu kini kita kena belajar pula solidification. Okay, nak proses, nak tukar daripada phase transformation jadi most of the metal alloy undergo this transformation before becoming useful object. So kita belajar pula dari segi solidification. Macam mana dia berbeku pula jadi bentuk solid. Okay, biasa solidification involve liquid solid phase transformation. Example of casting process. The solidification process differ depending on whether the metal is pure element or an alloy. Kan? Okay, dia cakap solidification process is different lah. Okay, kena tengok. We have to look each by one. Either it is the pure element, tak ada tampah, or an alloy. Okay, dalam case ni awak tengok the formation of stable nuclei in the melt nucleation, solidification of pure metal and alloy kan. Kena tengok juga the growth of nuclei into crystal ni, and the formation of grain structure. Bentuknya macam mana. Okay, jadi proses dia ada 4 lah. Start bermula daripada solution yang kita combine. Lepas tu nucleation of crystal macam ni. Lepas tu crystal growth, membesar growth crystal dia. Crystal ni yang mana? Yang kita belajar dalam chapter 1. Face centered, body centered, itulah FCC, BCC tu crystal lah. And the crystal grow together and form grain boundaries. Okay, ni proses-proses dia macam mana dia bentuk jadi solid. Okay, lepas tu macam mana kita nak study pula apa penting dia. Yang ni secara formation dia lah, secara bentuk dia, macam ni dia terbentuk daripada keadaan solution yang menjadi solid. Ni proses-proses dia. Yang ni macam awak kena ingat step by step lebih kurang. Tapi dalam slide ni tak tunjuk detail sangat lah. Okay, yang detail sikit dia nak tunjuk awak kena belajar dari segi cooling curve and phase diagram. Okay, sekarang ni cooling curve. Okay, cooling curve is used to determine phase transition temperature. Phase transition ni maksudnya pertukaran fasa lah kan. Pertukaran daripada liquid kepada solid atau solid ke liquid. Dalam case ni kita nak belajar dari segi solution liquid to solid. Okay, temperature and time data of cooling molten metal is recorded and plotted. Ialah dia ada masa, dia ambil masa dan berapa tempoh dia nak berubah daripada sini. L ni liquid, yang ni LS ni solid and liquid, and then finally you have only the solid, 100% solid here. So we have to record times. Okay, and then you plot the graph, and then you get the cooling curve graph here. Produce a graph known as phase diagram, which shows the relationship among temperature, composition and phase present in alloy. Okay, daripada cooling curve sini awak kena produce a graph known as phase diagram. Macam mana phase diagram? Macam ni phase diagram. Okay, ni phase diagram. Okay, tak apa, kita tengok satu-satu. Okay, jadi dalam case ni awak tengok A ke B adalah cooling of liquid. Dia dalam bentuk molten lagi kat sini, dalam bentuk besi ataupun alloy cair. And then from B to C, solidification begins. B here, so it starts to have the solid, and finally at C it should have only solid remains. At B, most of the liquid, only 1% or 0% of the solid, and then you start freezing here. Dia start freezing ni jadi bertambahlah solid dan berkurangnya liquid. So sampailah kat C, solidification ends, so habis. Jadi C ke D ni hanya dalam bentuk solid, dalam bentuk berpecah sahaja. Okay. Okay, a pure metal solidified at a constant temperature equal to its freezing point, which is the same as its melting point. Benda yang sama awak belajar dekat kimia masa form 4 kan, form 4, form 5, tapi masa tu eksperimen hanya simple mengenai air, pembekuan air je ataupun pendidihan air. Okay, sebab okay, benda yang sama kita belajar masa form 4, simple transformation process. Ni adalah temperature, ini adalah time. Satu buat eksperimen mesti sama je kan? Zaman awak zaman saya rasa sama je. Saya ingat lagi buat eksperimen hanya penuhi bangsa kat sini. Dan kita ada beaker, ada air, ini termometer. Okay, so ada jam randik. Seorang ambil masa lah, ambil masa. Okay, apa yang kita buat eksperimen waktu tu, masa form 4 tu, kita ambil transformation between the gas and the liquid. Okay, tapi sama juga, kalau gas dengan liquid pun akan jadi macam tu juga. Okay, sebab tu adalah 3 fasa. Setiap perubahan fasa akan terjadi benda yang sama. Okay, jadi waktu ni kita tunggu dia panas, suhu dia naik secara macam tu. Okay, sampai satu tahap suhu dia dah tak menaik kan, dia stay sampai satu tahap. Lepas tu air dah kering, air dah hampir kering, so suhu dah jadi macam tu. Tapi eksperimen hanya akan berhenti sampai sini lah, sebab kita dah tak ada kemampuan untuk record gas, record temperature kat gas kat sini. Okay, apa yang saya nak cerita, suhu bagi apa-apa elemen dia akan naik secara constant macam ni, sampailah dia punya freezing temperature or boiling temperature, dia akan maintain. Sebab waktu ni haba yang dia terima digunakan untuk pecahkan molecular bonding. Okay, sebab tu suhu tak naik. So bila dah pecah, dia pun 100% berubah jadi fasa baru. Kalau dalam segi kes ni, fasa apa dia berubah? Jadilah gas daripada liquid. Okey, jadi benda yang ni sebenarnya konsep yang sama awak dah belajar dekat form 4, form 5, SPM dulu. Sama juga dalam kes ni, cooling curve. Cuma dalam kes ni kita opposite side. Opposite side macam mana? Yang ni kita panaskan, yang ni kita sejukkan. Bila kita sejukkan, so temperature will reduce. Reduce pun constantly lah. Nampak? Sini. Reduce. Ni dalam bentuk liquid. Sampailah satu tahap suhu dia, melting point temperature or freezing temperature tu samalah. Melting point ataupun freezing. M ni istilah melting ataupun freezing temperature, benda yang sama. Sebab suhu dia sama. Dia jadi beku ke, dia jadi cair ke, pada suhu yang sama. Okay, faham? Jadi sampai sini dia kenapa dia constant? Sebab haba dilepaskan kat sini tak menyebabkan suhu dia turun dah. Haba yang dilepas kat sini menyebabkan bond between the atom and molecule dia tu, makin rapat. Sebab atom tu sendiri pun dah kurang tenaga. Sebab tenaga tu dalam bentuk haba telah dikeluarkan melalui liquid cooling macam ni. Melalui cooling lah, cooling process, melalui penyejukan tu. So apa jadi? So atom dia makin rapat. So dia waktu tu suhu tak berubah. Hanya proses nak rapat kat atom sampailah dia 100% jadi solid kat sini. Okay, lepas tu bila solid dia dah tak boleh nak bergerak rapat dah, barulah haba tu dilepaskan lagi menyebabkan suhu dia turun. Okay, tu je konsep dia. Sama je kan dengan ni. Yang ni untuk pemanasan, yang ni untuk penyejukan. Okay, that's what we call the cooling curve. Okay, so most alloy freeze over a temperature range rather than at a single temperature. Okay, alloy lah. Sebab tadi kalau pure ni pure metal. Pure metal tadi macam air kan pun pure element. So ni pure metal, dia tak ada problem. Dia ikut lagi konsep asal pemanasan dan pendidihan dan penyejukan, apa-apa yang kita belajar fizik dulu. Okay, cumanya bila alloy, sebab kita combine banyak elemen ni, dia dah berubah sikit. Most alloy freeze over a temperature range rather than at a single temperature. Okay, beza dia dekat sini awak tengok freezing begins kat sini. Sepatutnya kalau pure metal dia akan constant. Sekarang ni bila alloy dia turun juga sikit, dia tak jadi constant. Sebab tu dia kata freeze over a temperature range, not at a single temperature. Macam ni single temperature. Okay, jadi Untuk alloy awak kena lain sikit lah. Tengok apa yang berubah dekat sini. So ni kita kena take note or emphasize more on the freezing, where the freezing begins at what temperature and when the freezing completed at what temperature. So dari segi sini kita kena tengok pula composition ni, graph ni. Daripada graph ni baru kita boleh buat. Okay, figure A, phase diagram for a copper nickel alloy system. Okay, ini dah nama dia phase diagram untuk copper nickel. Okay, daripada copper nickel ni awak kena convert, dapatkan cooling curve untuk copper nickel ni. Tapi dekat mana? Based on apa-apa composition lah. Contoh dia kata kat sini, yang B adalah cooling curve untuk 50% nickel and 50% copper. Tengah-tengah lah kan. Copper sini 100%, sini nickel 100%. So tengah-tengah dia 50% nickel, 50% copper. So kita tarik line sampai dapat jumpa kat point kat sini. Saya tukar warna. Okay, satu line kat bawah ni line apa? Ni line solid. Yang atas ni line liquid. So belah atas semua liquid, yang belah bawah ni semua solid. So jadi kita tarik dia project ke kanan. Tapi make sure graph ni sama betul-betul align tarik kanan, so kita ada satu point. Ni adalah solid. Bila dia dah jadi solid, waktu dia solid ni lah kita panggil dia freezing, dia dah selesai, completed. And then here when it starts to freeze, ni limit kepada liquid kan, nak berubah bentuk dah. So kita tarik dia, tarik dapat satu point kat sini. Okay, cumanya point ni mungkin awak boleh tarik ke sini, tapi kena straight lah, atau point kat sini. Okay, ni depends on your graph juga. Kita nak kena tahu berapa time allocation dia. Kalau time allocation awak tahu, awak boleh tarik lah nak mana-mana, tapi must be at the same horizontal line dengan point kat sini. Sebab ni nak menunjukkan, okay, ni dia bermulanya dia freezing, ni dia berakhirnya freezing proses, pembekuan proses. Okay, so macam itulah awak akan tarik. Okay, yang ni bermulanya bila nak pouring temperature tak ada masalah kan. Awak kalau tahu pun mana-mana pun boleh letak lah kat sini, suhu mana-mana kat sini. Sebab macam mana pun kita pouring masa waktu dalam bentuk liquid. So as long as it is in the liquid region here, so it is okay lah. Tak payah nak ambil daripada maklumat sini. Okay, tapi mesti lebih daripada 1455 lah suhu dia. Sebab kalau 1455 dia dah dalam keadaan solid. Ni tempat dia cantum solid and liquid at the same critical point. Okay, macam tu harap-harap boleh faham lah. Okay, jadi development of phase diagram, macam mana dia nak bentukkan phase diagram ni. Okay, cara dia, dia kena dapatkan banyak cooling curve. Okay, series of cooling curve at different metal composition first constructed. Tengok kat sini, dia ada banyak. Satu yang 100% copper, lepas tu 20% nickel, 50% nickel, 80% nickel, and last sekali 100% nickel. Jadi maksud kat sini, kalau 20% nickel, so ni adalah 80% copper, yang ni 50% nickel, yang ni adalah 20% nickel, and then this is the 0% of copper. Ni copper lah, silap. Jadi dapatkan banyak ni daripada mana? Daripada eksperimen. Daripada eksperimen banyak-banyak ni, kita pun tarik lah jadi dia punya phase diagram. So ingat lah, yang ni nama dia phase diagram, yang ni nama dia cooling curve. So daripada cooling curve banyak-banyak, awak pun boleh tarik. Saya try lah tunjuk. Okay, ni yang ni bila 100% kan kita tahu dia constant temperature secantik. Yang ni adalah freezing dia, freezing point dia. Jadi macam tu. Oh lah. Ya, agak-agak lah tengok lah. Okay, lepas tu yang ni, okay, ni freezing point untuk 80%. So awak bertarik straight. Macam mana saya tak boleh straight ni? Hey, apa Microsoft ni? Aduh. Okay ni, siapa yang tak boleh naik atas tu juga? Tak boleh lah. Boleh pun. Awak faham lah, lebih kurang macam tu lah. Jadi start line ni S3 pergi ke S3 sini, L3 ni pergi ke L3 sini, and then so on sampai lah yang dapat 100% copper, so dapat kat sini. Daripada situ awak buat curve dia, sebab jadilah nama dia phase diagram untuk copper and nickel. Okay. Jadi yang lain tu baca lah, and then habislah untuk subchapter 2.1. Nanti saya akan buat video untuk subchapter 2.2 juga. Jadi awak boleh baca sendiri, tak payah ikut waktu kelas. And then hari Jumaat ni, next Friday, on 7th of May, we are going to have the quiz one that cover all the chapter 1. Okay, it's only on the multiple choice question, and just 13 question if I'm not mistaken, and the time duration given for you is only 50 minutes. Okay, so we will start the quiz on 8:30 AM. You have to log into Island and find the quiz under your group, under my name. If you have the problems on that time, you can ask me directly through our WhatsApp group lah. Okay, so I hope you enjoy our video today. And material science is quite a bored subject, boring lah kan, but this is one of the core subject for a mechanical engineer, because you have to know, you have to study about the material itself. Jadi nak tak nak kena belajar lah, kena baca, kena ingat. Okay, so till the next video, till the next class, take care yourself. Assalamualaikum and bye bye.